Welcome to part 1 of the Glacier Mass Balance lectures. My name is Andrew Mercer, and I will be giving a brief introduction to the basic processes of glacier mass balance. This chart is perhaps the most well-known product of the monitoring program at Tarfala Research Station. It represents the end result of a great deal of work carried out by a team of researchers and workers, and summarizes the year-by-year surface mass balance of Storglaciären in the Kebnekaise Massif of northern Sweden. If we start at the left of the chart, in 1946, the white bars sticking up from the zero line represent the winter accumulation, i.e. mass added to the glacier. The grey bars represent summer ablation, i.e. mass removed from the glacier. The next bar, in this case, is red and points downward. It represents the year's net mass balance, which was negative, hence the colour and direction. Following the chart along, each year's accumulation and ablation are added and give the net balance as either a blue, upward pointing bar for positive net balance, or a red, downward pointing bar for negative net balance. It is quite evident from the chart that the net mass balance for Storglaciären has been generally negative, though we do see some periods of sustained positive mass balance, such as in the 1990s. The cumulative surface mass balance shows the trend, and we can estimate the average loss of water equivalent over the glacier as a whole to 18 meters. And one more feature of this graph that needs to be noted here is the unit used for mass balance, meters of water equivalent. That is, convert solid state mass to liquid and then declare the column of water at a point that is gained or lost. Where does data such as the Storglaciären mass balance series come from, and what physical processes does it represent? To start with, we must simplify our study. We will not yet consider carving glaciers or ice dynamics as such. We will begin by looking only at land-terminating glaciers. We will not discuss basal processes such as geothermal heat flux, which can cause basal melt. Nor will we consider internal processes of ablation and accumulation during part 1. We will limit ourselves to surface mass balance processes, which are easiest to measure and have by far the greatest contribution to total mass balance. Let's start by familiarizing ourselves with a very simplified and greatly exaggerated profile through a land-terminating glacier. We will also ignore, for now, any consideration of thermal regime. The main bulk of the glacier consists, rather unsurprisingly, of glacier ice. This ice flows from the accumulation area to the ablation area, under the force of gravity. The accumulation area consists of that part of the glacier where the net balance is positive, i.e. mass is added to the whole. The ablation area, conversely, consists of that area where the net mass balance is negative, that is, mass is removed from the whole. Separating the two is the equilibrium line, where mass balance is zero. There is no net gain or loss of mass. Accumulation and ablation are in equilibrium. At least that's the theory. So let's look at the accumulation processes. In the case of Storglaciären, and indeed most mid-latitude glaciers, the winter season is the accumulation period. Snow falls often over the entire glacier, even if with varying magnitudes, and this snowfall is greater than any ablation that might occur due to brief warm weather events causing melting and evaporation, or the continual process of sublimation directly from snow crystals. The distribution of snow accumulation is a complex process, and is dependent on direct snowfall, wind redistribution, compression, and avalanching. Some glaciers may only show accumulation on parts of their surface, and accumulation events can occur at other times of the year. But the general model for mid-latitude glacier accumulation is the blanket falling during a specific season. Tropical glaciers tend to have more sporadic accumulation, both in time and place, whilst high Arctic climates allow near constant accumulation in some areas. At some point in time, winter turns to spring, though this may vary along the glacier. and at this point ablation becomes the dominant process. In the sketch shown here, the snow cover has already been removed at the lower section of the glacier. This may be due to wind redistribution of cold snow, or more commonly, it may be caused by melt. The snow lying beneath the bare patch at the front of the glacier is a common phenomenon and is a result of topography and prevailing wind direction producing increased snow depths at the front, a so-called snow apron. As the spring and summer progress, the snow cover retreats further up the glacier. The point at which the ice is exposed by retreating snow is called the transient snow line, and represents what may be thought of as a very short-term equilibrium line. Should the ablation season end, this line will mark the divide between the current year's ablation zone and the cumulation zone. Remember though that the long-term equilibrium line and zones are not as easily defined, and are average values based on many years of varying weather. The firn layer may be exposed. Firn being that snow which has survived through at least 1 year but has not yet become ice. As firn is not glacier ice, the firn line, if exposed, indicates the long-term equilibrium line, though this may be considered a matter of definition given the continuum of forms that make up a glacier's mass. In very negative years, almost all snow cover may be lost from small glaciers and the firn layer exposed to surface ablation. We might then wonder where the equilibrium line truly is. We must always bear in mind that a glacier responds to weather and climate at multiple timescales. Remember also that the transient snow line may not be a reliable indicator of mass balance. The ablation gradient may be unusually steep or snow cover unusually deep at higher elevations. The total mass balance is the sum of mass in and mass out. Looking now at a graph depicting the average values for the winter and summer mass balance components, for 20-meter elevation bins on Storglaciären, we can see how these vary along the glacier's elevational range. Note that both components are measured and plotted as positive values, but the net is calculated from BW minus BS, which we will look at shortly. The profiles plotted here are long-term averages, and so the point at which they cross represents the equilibrium line altitude, here at approximately 1500 meters above sea level for Storglaciären. Looking at the profile of the summer balance, the ablation gradient, we can see an approximately straight line with negative slope. The actual profile does diverge from this line at certain elevations, mostly due to topography and specific distribution of area at elevation in Storglaciären. The winter mass balance profile is not as easily modelled. Using two straight line functions we can approximate the curve, but it is quite clear that even this is not precise, especially below the equilibrium line. The net balance curve, derived from the winter balance minus the summer balance, is then the summary of these. The net surface mass balance for Storglaciären exhibits a generally decreasing trend with elevation, but the trend towards less negative values near the front is apparent. If we look at the accumulation profile, we can see an increase in this region compared with higher up the glacier, but also a slight decrease in ablation close to the front. Lastly, a word on terminology. In the last few slides, you may have noticed different terms being used for accumulation, ablation, etc. The International Association of Cryospheric Sciences Glossary of Glacier Mass Balance and Related Terms has compiled a standardized list of symbols based on usage in mass balance literature. Lowercase letters are used to represent values at a point, whilst uppercase letters represent glacier-wide values. Subscripts are used to clarify further each term. Thus, often B subscript W can be seen as equivalent with C subscript SFC in the Storglaciären mass balance calculations. In part 2, we will look at details of accumulation.